Hi everyone. I'll be talking about Lean database. It is something that we were working at Emergence for some time now. Right. So Lean database, we are trying in this project, we are trying to formalize relational databases in Lean 4. This is the team as of now, like Siddharth, me, Anirudh, and Datta, who's not here. Yeah, this is the repository. So yeah, what are relational databases? A lot of information in the world is being stored in relational databases. It's just, you can just think of it as a table, right? Table with many rows and you have columns. And then you can have multiple tables having relation to different, like you can have multiple tables which are related to each other. And many of the data is stored in such structures, and we interact with these relational databases through SQL queries, right? And it's a very common method. That's how we talk to the data, and it is how data science, data engineering, analytics, many industries and in many areas, this is the thing. This is the thing how you talk to the data. And yeah, this is an example of an SQL query. This is how it looks. I mean, just for people who have not seen it. So why is formalization interesting in this area? Right? Because almost every query can be written in more than one. And you might want to rewrite a query to make it more performance efficient, or you want to rewrite a query so that it makes easier for a person to read, right? To understand what you're actually retrieving. Right? And the issue is how would you, like given a query, you might ask an LLM to make it more performance efficient, or you can ask to make it more readable, right? Human readable. But then how would you know that it's actually equivalent? How would you actually know that it is equivalent to the original? So this is where formalization would come. So we try to prove the equivalence of queries. That is one part of it. And here I'll show you a few examples where you have two different SQL queries that are equal, that is being proved by our system. So the first example is this. You have this table. You have three columns: age, which is an integer; is active, which is a bool; height, which is a float. And you have these two queries, right? I mean, this is quite easy. Like this is just De Morgan's law. So you are selecting from the table where age is not greater than 30, or like, yeah, I mean, where not age greater than 30 or is active. So it's not A union B is not A union not. Right? That is what we are trying to prove. And this is how the proof would look like in Lee. Right? This is how you are representing. And just we'll look at this a bit later. And yeah, so this is the query, and you're proving that these two are query, and this is the statement of your theorem, and this is how you're proving. You just
SQL percent is our own notation.
Yeah, this is our own notation. SQL percentage and table underscore schema. These are all our notation, and like you just create this table. Again, there is a syntax to create a table, and then that would store it in this variable name table underscore schema, and you're just saying a SQL percentage. It is to this database that we are applying this query, and here we are doing this. Are these equal? This is the question, and it proves that these are equal. Right? I mean, that was a simple query, and like you have another one, which is just saying that if you select from a union with some filter is same as selecting from each of them with the filter and then taking. So here this might be a bit more performance efficient because you can parallelize these two things and then take the union later. So again, the proof would look something like this, and this is slightly more complicated. And yeah, you have now two tables, and then you are doing certain things with like actually the relation between two tables, and the proof also.
Can we view these SQL values as functions? I know, right?
Yes, exactly. I'll come to that. Yes, that's exact. In fact, if you go back here, if you look at what we are proving, you see this thing, right? Like these are two functions, right? Which we are trying to prove. Like for example, this is a function from this to bool, right? Yeah, and you're trying to prove those two functions are equal. Yes, part of it. Yeah, it's slightly more than that. Yeah, extensionality. I will look at the. So if you one thing you must notice that every proof is a single tactic, right? SQL equal. This is something Anirudh wrote. Like it's a bunch of tactics just stitched together. And you saw this example of repeat first apply, right? It's that tactic. I mean, slightly more. Like I'll show you the tactic at the end. So yeah, so this is another example. This is slightly more involved. So there is join, there is on, and then there is nesting, and it's a slightly more complicated queries, and these are equal. Again, it's proved by SQL. I'll just show you one more. Yeah, this is written this is quite complicated, and this is very easy to read, and like the system actually proves that. So it has an info view inbuilt in the slides itself, and yeah.
I've not seen this so.
Yeah, like even I found out yesterday. So So yeah, so how does this actually work? So what is exactly so you have these layers, you have data model, like how do you actually look at the tables? What are the tables? Operators, that is there are selection, you have to do join, you have to do group by, and then you have a parser. This is all meta programming, and this is how so you can see that here you're actually writing these queries in SQL, right? It's a SQL, you're writing it in the SQL language. And so you want a system to parse that SQL text into actual real line terms. This is all meta programming. And then there is this SQL equip tactic. I'll just go through fastly. So a column is encoded in the definition of a definition, which is called type tuple. So this is basically what wait, it's not a column, it's actually a row. That's a mistake. So a row is, so every row, sorry, you have finite number of columns, and each one of them can be of some type. Like, well, some of them can be nat, some of them can be string, some of them can be pool. So you're basically saying, you're just tell them what the type of the row is, that what is the type of every column, and this is actually telling you what is there in every. And a table is encoded in the structure of typed relation. So it just gives you labels for the columns and it gives you rows. That's basically the set of tables. And this is how you construct an empty relation, right? Like you give labels to be some labels and rows are just an empty. Right? This is how you model tables. And here, like some operations, a union of two tables, let's say it's just union of rows, labels remain intact. So union is just stacking them one above the other. And then restriction, which is if you want to, so this is basically what where uses, right? Like you look at every row and check whether it satisfies some predicate, some property, and then you just filter your rows using that. That is restriction. Similarly, projection. Right? You are projecting onto certain restricted number of columns. And you're just selecting specific columns. These are the definitions in Lean, and these are the examples of theorems. So you are proving that union of rows. Yeah, the rows in their union is same as the union. Rows in the union of two relational databases is same as the union of. And there is another theorem which says, this is basically partitioning. So you are filtering something with respect to P and with respect to not P, and then taking their union is same as just taking the same title. This is a theorem which proves that. And yeah, here are some more.
So the grind annotated means that SQL tactic uses all these theorems.
Yes. I'll show you the SQL tactic macro. Yeah.
Now the annotation is saying all these theorems are used to actually prove queries are equal.
Yes. So these are the parts which ultimately go into proving the equivalence of queries. So any two queries are equivalent with respect to these some kind of rules, right? Like you might have this kind of thing happening or this kind of thing happening. So these are all the so grind. When you use grind, it checks whether this theorem can be applied to this particular situation to prove equal. Matrices, no, but I don't think you cannot have different types in a matrix, I guess. I don't know what.
All the entries are the same type.
Yeah, all entries are the same
type. Database,
yeah.
One entry is a string, another is a bool, another is a natural.
And also we want to have labels for, I mean, it's better to have a actual table structure than just giving it a matrix structure. And we don't have any extra importance. We don't need inverse of a matrix, for example. That's just extra structure we get. So we are not actually using Lean to query a database or anything, right? This is just we have not loaded even like a database into the. We just need the metadata of the database as of now. I mean, like maybe we can. But we are not actually querying using.
Ready? The schematic check the cut for the including. I mean, wanted to do this kind of query.
Yes. So, I mean, in practice, this would like you just give queries to the Lean system, and Lean would verify if these two queries are things. You just give the metadata of the relational database, and if database has some properties, let's say if it has some specific properties, you can just give it as a hypothesis to the Lean, and then you're just proving these two are equal. Just those two queries
equal as functions.
Yeah. So basically, any query is nothing but it's a function from a relational database to a relation. Huh?
That was saying about function extension here.
Yeah.
So it's equal as that.
Yes.
Equal as function.
So these two the queries are functions.
Will be. Yes.
Equal
mathematically, they happen to be functions. So you have to say the right hand side is equal for any input. But that will involve non-trivial amount of work sometimes.
Yeah.
To show that equal.
Yeah.
But it is function extension then.
Yeah.
Queries like SQL syntax is like a shallow embedding or
Shallow and
Shallow stuff. Yeah, I think I have slides about how the SQL set up. Yeah, so there are many theorems like this, there are definitions, theorems, there is a whole bunch of theorems which the grind uses and SQL equipped tactic uses to prove the equivalence. Now, this is one, I just copied one snippet of how the syntax is embedded. So yeah, so you have this embedding, and this question mark means you might have distinct or you might not have distinct in the query. Similarly, you might have having, or you might have this whole, whole snippet. And we have defined a new syntax category called SQL query. And these are all different syntax categories which have been defined. This is how you embed something as a domain specific language. And this is the main function. I mean, this is the main function which tries to elaborate the SQL query, and and then we try to prove it. And yeah, this is the tactic, right? I mean, you have this SQL equipped tactic which has that repeat first style that you saw, and these are all the things that it's trying. Right? SQL simp is just simp all this, and it is opening up type relation, the definition of type relation, and yeah, it's trying a bunch of things. So I think this Anirudh tried to solve a lot of examples and then saw what are actually being used most of the time, and then just stitch them together to make this tactic. And yeah, no, like we are just doing this. Like if you have an SQL query, right, and the same thing could be queried in a different way. I mean, they might not look similar just at glance. So now you are embedding these queries into Lean, into the language of Lean. Like you are making functions basically, because query is mathematically a function. Then you have two functions, and you're proving these two functions are.
But you do between bias, see what sort of BSP mean.
No.
Or I said,
BSPs are often quite different
As
in the example series, but they're the same query, so they're the same functions. So yeah, so they're not the same ASPs. It's the actual function.
Oh yeah, you're not looking at the syntax tree of the function. Is that the question? Like,
Yeah, that was the
oh yeah, you're just proving that those two are same, like equal leaf terms or something.
it use assembly solvers or just this,
Grind uses SMP solvers.
grind is itself a small SMP solver inside.
Yeah, so it is some things are happening.
When you scale up, we may starting working Lean SMP. So far, grind is not enough as a.
it's just the checking functionality. But
Yes.
like an input and guessing it would be scoping and see how kind imitate functionally equivalent how do they perform. If you're taking in SQL, there's a lot of performance optimization.
Yes,
factors.
yes.
Taking 10 versus taking 15 in a particular query. And I mean, what do you think? Like, could that be done?
You have to encode somehow what good performance would mean in Lean, and then see with respect.
It's not just running it. It's the query itself. You can have different ways of having a single query that performs better.
Yeah, so you should have a formalization of what performing better would be, right? To say one performs better than the other, you should have a formalized, like, yeah. I mean,
Number in general, symbolic reasoning is not great at judging correct.
150 meters.
It's good at judging correct.
Yeah.
Something.
It's better because run is
Yeah.
very cheap of numbers.
Yeah.
Sorry. What you can do is you highly optimize maybe some person or LLM, and supposedly highly optimized, you check if that really is the same query or the highly optimized anything.
To simpler, can we somehow use Lean system to kind of reverse this and search in the space of equivalent queries? So like apply all these rules to kind of like generate a bunch of queries that are all equivalent to my original.
Oh, yeah, maybe.
Maybe you can.
Maybe you can, yeah. Yeah.
Actually, support advanced like can it come on with the semantics for advanced maybe yes. Also,
Oh, so I don't know much of this. Yeah. You can ask that. Like,
does it support advanced SQL, like PLSQL?
No. For currently, it's a basic SQL. Currently, what is common to all SQL dialects in common use. This is after, I mean, basically, you've been, I mean, more intensively, say, like 3 weeks of work. So, yes, I mean, it's very much extensible. That's the nature of the language, but it will take work. So, currently, it's any feature that it seems to be most dialects of SQL notice.
So then I'd like to know what are the settings is to case and with.
If you want more complicated, it can always be extended.
we can keep on adding all those things one by one. These are all just adding. We have this basic data structure that is type relation, and then any query is just a function between type relation. And then you just have to add any new kind of operation to be a function which does this, and then prove some theorems about it so that it can be used in proving equivalence. Yeah, so this is the SQL equal tactic, and yeah, what's next? What are some directions? So we can use, so now as of now we can prove equivalence, or it can fail to prove equivalences. So we can have use plausible, which is a lean library to use to prove. It's a tactic to prove, like actually find counter examples. Given to queries, you can actually find counter examples that proves that they are not equivalent. And the other thing is, this is just proving equivalences. We could actually somehow have a safety verification framework included into this, which says SQL counter example, like given two queries. Counter examples would be, it would give you some databases where these queries are not speaking a base. Yeah. Or given a database, it finds out something. So yeah, this is the other thing we could do. Like we could, yeah, because SQL injection is a serious threat, and then you can have somehow formalize what safety means and then give certificates for SQL queries that they ask. The other thing is expanded automation. Like now we can prove more theorems and annotate them with simp and grind, or actually improve the SQL equal tactic with some meta programming, and then so that it could even prove more difficulty. Yeah, so this is a server that yeah, Siddharth made, and this area here you can just name your table something, and then you can give column names and their types, and then you just enter your two queries and click check equivalence. The Lean will check equivalence for you. It will apply SQL equiv and try to prove that if that is, like for example here, we can just take this example, right? You have these 4 columns with these types, and then you have these 2 queries, and yeah, it sent us JSON to Lean, and this JSON is parsed and given to that function that I showed, and it parses those 2 queries and then makes the theorem that they are equal and tries to prove it by SQL. And if it proves, then it shows that they are equal. So you can see equivalent true. So this is a very convenient way to test, and something which, yeah.
Here the database is finite.
Yes.
Domain is finite.
Uh,
You can just enumerate anything over the domain, and that's compare the output of both the query. That will mean they are even on this data.
Oh, but you want it to be independent of the data. I mean, you don't.
Here the database speaks. It's not here.
No, here's a database schema is put, not the actual data.
Yeah.
It may be the census data of the country that you're making.
Oh,
very
we are fixing the types of.
Yes,
yes.
schema is. And this is a mathematical proof of equivalence independent of the actual data.
So these queries are equivalent.
Otherwise, you would just do the queries and see the answer.
Yeah.
This is true independent of the actual data. Just
I also independent the size of.
yes, independent of everything except what the columns are.
This is the only data you're giving, right? I mean, you're just saying there are 4 columns, and each column has these types, and these are the queries. Are they equivalent? You don't know how many, like there might be like millions of rows. It doesn't matter. These things, you don't have to load the Lean data, like the database into the to Lean to for it to prove this.
System still have false negatives, right? So it means that if they are not equal, like they could still be equivalent, but the acting is not 100%.
Yes, that can still happen. Yes, yeah,
That will not.
that will happen. So yeah, I showed you the tactic, right? Like this structure.
Saying more time.
Yeah, I mean, like you could.
Yes.
Yeah, you could actually write down, like there might be certain cases where you could actually write down the proof, right? I mean, in principle, yes, there is always a proof. Yeah, I mean, like it could be improved. Yeah, I mean, yeah, this is the tactic. It does all these things. It tries all these things in a particular order and checks whether.
So let me say that. So you've heard the term again when we were discussing Raghavan also. So you push button or not, right? So this is supposed to be part of a Python pipeline. That's why we serve the JSON. So we want push button automation. So we have one tactic. Now, nothing stops you from using this where it fails. It will give you the Lean statements as if I'm getting feedback. But the intended use case is exactly a push button, fully automated as part of a pipeline. So for that, it has to be one tactic. On the other hand, this SQL equivalence is another put it together fairly quickly now. Linear, which I see we are working on there. There's a much more sophisticated automation. So we can put much more sophisticated automation, and over time we will strengthen this. But we do want we do probably want protected because it's supposed to be push button rather than interactive. That is the.
If it fails to prove, you get the actual thing you have to prove, and you just sit and use the theorems, the existing theorems, and try to prove it.
In this case, one aspect because you are a particular way of proving any device.
Is there theoretically a particular way of
Yeah.
proving any equivalence for relational databases?
As grind differs a lot. It's the secret of
Yeah, but it's so that it's not a theoretical clever algorithm to prove equivalence of queries. It's not. It is not that. Yeah.
this is the best effort tag.
Yeah.
It is not a universal one. This is the best effort tag.
I don't know if there is.
Best effort is fairly good as it turns out, and most of the credit goes to grind as possible.
But
And
I
also enough theorems have been proved by Adya and Aniruddha, also some by Datta,
Datta.
and annotated as grind. So enough manual work has been done so that grind has things to work with. And given that it has worked, yeah, and also Aniruddha has put the specific refine and outline. So enough manual work has been done to help grind, and grind is very smart.
Yeah.
So those are the two ingredients why, but it's very much a less.
But I think. But if your question is there an actual, like, if given two queries, is there an actual algorithm to prove whether they are equivalent or not? I don't know.
So, hi everyone. I am Anirudh Gupta. I've done my third year BTech here. So, so I will be presenting a project that we have been working as part of Emergence and ISC internship, which is called Pastaline. So, Pastaline, as you can see, it is transpiling and verifying Python in Lean form. For those who don't know what transpiling means, it means converting a language into another language. That's all. And of course, verifying is the theme of the summer school, so I don't have to go about it. And main part without LLMs. So a lot of people just think of LLMs these days, and because it's very hard to convert one language into another, which it is actually, and this project was not easy. So yeah, go ahead. So what four things I'll be talking about is why even verify Python at all, right? Why in Lean? Well, I don't have to answer why in Lean because I think by now you guys have a good idea. And how Pasta Lean works and how does it convert Python into Lean? And what we all support right now. I mean, you can obviously guess Python is super bizarre and it can literally return list in one branch, integer in another branch, a dictionary in another branch. And Python is statically typed, so you can't do all that. So there is a limited subset we support, which we have tried to increase as much as possible. But for practical purposes, like the codes which we use for data science and all, those are well managed and behaved. So I think for those, we are good to go. And proving, obviously, proving the generated code is it correct or not, and what we will do. So what are we cooking today? Right, pasta plus Python plus Lean, and we get pasta Lean. So if you recognize this, this is AST. So we convert Python to Lean using abstract syntax tree, and P is the spoon, and this is for all Lean, right? So pasta for all. Okay, and yeah, as I said, so how to use Python to Lean is basically rough idea. Take an ordinary logical Python, the kind that data science and practical logical codes LLM actually writes. So no point in converting stub code like data set loading and calling this and that. No point in that. The main part where Lean would help is actually the logical side of the code, like the algorithms that you would like to convert, right? So we do some pre-processing with Python code, which is basically adding some type annotation, which will help, and obtain its abstract syntax tree and give the Lean its JSON format. So abstract syntax tree, JSON, give it to Python. Sorry, give it to Lean. And of course, then we transpile it to Lean 4 and deterministic tree without LLMs. We convert into a Lean 4 version. And something is written there at the bottom, which is, yeah. So the goal is basically write it in Python and get the guarantees of a proof assistant. Okay. Right. So why do we want to convert Python into Lean? So two most booming things in today is Python and LLMs, right? So everyone uses LLMs to convert to write Python, and new languages like Lean 4, many LLMs might not be so comfortable in writing Lean, right? But everyone is comfortable in writing Python. Even the small quens and all are good in Python. So why not? And if you want to verify these things, you will use Lean, but converting directly to Lean is a bit, rather writing in Lean is a bit harder for these LLMs. So this tool is the inspiration for using the logical codes that other LLMs, small to large LLMs make, and then we just convert to Lean. All right. So who checks the generated code, which is actually correct? We have to do that in Lean. Right. Okay. So why Lean? Everyone knows. I don't have to go into why Lean we need. So why convert into Python? Blindly trusting LLMs Python means you are shipping logic no one has proved, right? And silent wrong answers can really mess up your code, right? So we basically basically try writing it in Python and trust like the Lean has written the code and we use it with the same guarantees that the Lean is correct, then the Python is also correct. So few questions, why transpile and why not just ask LLMs? And well, obvious answers. Well, there are a couple of methods that people can convert Python to Lean. One is ask LLMs and one is use pasta Lean. So there are a lot of disadvantages and advantages. Basically, LLMs can hallucinate. They might not be reproducible codes, right? So it may take a long time to create large pieces of codes, and there is no ground truth that it is correct. And by now, you know that testing is not enough. You need to have proper formal method logical verification to check if it's correct or not. So these are some inspirations of why we are going the way we are going, right? There are some things like other methods possible. So there are a couple of more methods about checking this. One is like testing, and you know that testing is not enough. Then one is that there is something called lean.py, which is an FFI from Python to Lean. So that is possible. You can convert Python to Lean using lean.py using FFI. But then you're basically at the end, if you know FFI, you're running a Python code pair. But then how will you do a verification on that? Because you need to express everything in terms of Lean representations than a Python code. Okay. So let's start the real understanding of how pasta Lean works. Is there a possibility to reduce the font size? So this is a regular, the simple Python code, which is sum to n. Forget these statements for now. The invariant ensures required. So if you recall Elias Haji's talk, you will recognize what these are. Forget about the sum. For I and ring n to 1, you just add things up and you return the total sum. That is sum to n. Plus, what we do is we use Python's AST library and we convert into abstract syntax tree. And then one question you can ask is, well, this is a Python library, so it might be incorrect, right? Well, Python itself uses this, and a lot of good developers have been fixing bugs on this. So I think we can trust this. I think it's like well tested. And then we transpile it to something called def sum to this looks like Python. And sorry, this looks like Lean. So we have our implementation of range, our implementation of these contracts that we write, and many more. And then the last goal is that we want to prove automatically. And this is not written by me. This is automatically done, right? So this is theorems sums to n that if you recognize this little bit, I'll just. If you recognize this part, this is a whole triple, right? So for monadic proofs, we use whole triple verification logic. And based on the ensures that we use, the ensures become the thing that we have to prove, which is 2 times total is n into n plus 1. It automatically proves this. Okay. So again, the proof is not done by LLM. It is done best referred by a tactic that I wrote. And one more thing, apart from just proving, you can compute also. Right. Yeah, go ahead.
Two questions. One is requires and ensures if Python is it's part of the language itself. Is requires and ensures part of the Python language itself.
No. So this is one extra thing from Python that I had to do. So I just wrote a simple like 15-line code, which is like ensures, requires, and something. So these contracts is the only thing that LLMs add in my code. That's all, which I will talk at the end. So using that small 15-line code that I passed to LLM, ki, ha, these are the ensures and invariants, try to come up with them and then put in the code. This is written by me, like manually put by some extra Python things that I write. You can use other libraries for contracts, but I mean, I didn't feel the use of them, so just put it manually. And these are extracted manually by us into Lean. Yeah, does that answer your question?
Yeah.
Just mention there are standard Python contracts.
Yeah, there are
Not-
standard. You
which
can
we might
use.
switch to at some
You
point.
can use
For people
Viper
like
based.
agents like
based.
Jeremy and so on use.
Yeah, there are libraries, so you can do that. But I didn't feel the need to use all that.
Determined by the requirements. Internally, whatever the Python program does doesn't have to be what the Lean program. I can do whatever I want as long as I get the correct results. I don't have to faithfully translate the entire program step by step. I just need to get the result.
Yeah, you need to do that.
So any program which gives me the result is a correct translation.
So you don't see.
That's
Firstly,
it.
you have to.
No, the transpilation is deterministic.
Okay.
Transpilation is Lean code which actually generates this loan. Lean metaprogramming generates this code. This is not LLM generated.
Yes, the question is how faithful is the translation
No.
to the Python?
Yeah, it is.
Because it's a deterministic code, it can be tested.
Yeah, it is a very
It's
deterministic
one
code, and
piece
we
of
can fix it
deterministic.
every place. Then I tested like CP problems on this. So I think I got 80-90% done. And that 10-20% is not the correctness issue, but the support of Python into Lean.
Okay.
That was incomplete. So, but 80% of the test, like CP problems I tried, they were correct.
Just confirm the line.
Yeah.
Hasty part.
Yes.
Implementation same.
Yes. As this. So this is converted to a JSON version, which Lean can easily read. And then we stitch it up. That's all.
As instead of using the faster Lean libraries.
Yes, metaprogramming also.
What do you need for the program? Programming your authentication conditions. It's
Yeah. So there are two tests we did. One is the breadth test of Python to Lean and how good our API is. So if you notice that we have written this pi range, and when you see later on, we have pi list, pi dict, and so on. So for list, dictionaries, zip, enumerate, everything we had to write manually, right? So we need to make sure that those are also behaving like how Python would behave. So that's a pretty manual task. So for those, I use CP problems and tested it on all those test cases. And if Python is correct, then Lean is correct for sure. So I have to. So for CP problems, I don't need those requires, invariants, ensures. I just need to eval and check. But for theorem proving part, I would need those.
it's like from yesterday about some issues which are like logical, some are like memory based and stuff. So the what you're doing, like the checking that you postpone the second thing. You know.
Only logic, not low level.
So what if turns out that the proof doesn't work?
The-
Sense that invariant that you're whatever.
It's always best part, right?
Okay, no, once again. So then can you, so essentially what you're trying to, so two things are essentially happening. One is that invariant, that ensure statement is in fact not right. It's possible.
It is very much possible.
Or there was some problem with the transcription. Suppose we ignore the second problem. Can you go back and trace which of those statements are actually, I mean, how would you debug a program based on the output?
Yeah, you can debug it.
Yeah. So essentially the question is it what do you call, is it easy to go back and track
Yeah.
the source of
Yes.
where something went wrong?
Yes. The way I have structured that architecture of the code base, I will show you. It's very much easy to extend everything and debug. Very easy.
And sorry.
So you constructed like so you use the AST library to get the AST from the Python code, right? So for the AST to Lean, how did you do it?
AST to Lean. So AST we first, for per node, we need to create a JSON for it because Lean has easy JSON readability. Like some libraries are there. And from JSON, we pick each node one by one and then stitch it up. Like literally, if you see function def, we have compare, assign, the name, type, for everything is mentioned properly, right? So you just stitch them up.
So the AST to Lean transpilation was done by like humans.
Yeah.
Okay, and you have like a fixed vocabulary, right? So which maps from Python to Lean.
Okay.
So you take all the keywords in Python and then like you have them in Lean, but like if there are like any like new additions or like libraries or that sort.
I will talk about libraries, but I have not covered all Python, though, right? This is like a 2 months project now. So you can't expect me to cover all Python. So
But also the ST elements are fixed. We have more and more functions in.
yeah, by the way,
But the
ASP,
structure of a Python program is a fix.
you might
That
do
is
anything
covered.
but fancy
It's
semantic
not something that-
syntax writing with Python to make it as optimized, but the AST will still be as long as it needs to be.
And on the other hand, also I should say the Lean knows
Yes. Oh, it works for classes. It works for OOP. Just wait. Yeah. Yeah.
What if very research it will not sufficient to actually prove the value.
That is separate problem. Okay. See, the part of ensures and requires. I'm right now in my stages expecting LLM to work properly. But again, as your point is correct, that the more the better the theorem statements you want the theorem and proof to work, the better and more correct ensure statements you have to do. But that is a problem that I have not tackled yet. This is a very like last week or last 2 weeks thing related. Yeah.
I have a quick thing. I think it's extension what
Yes.
thing, right? So um if your theorem if your theorem concludes that is proof, right?
Disproved it can't.
No, I meant to say it's not able to prove,
Yeah.
right? It means that either your ensures and requires are available, yes, or the implementation is wrong.
Or it's not able to prove it.
That's how we have to look at it.
Yes. I can't. I don't know how I can write a theorem for guaranteeing that the transpilation is correct. I think that that theorem would be impossible to even construct. I think. I don't know.
Well, not impossible, but you'd have to write a full Python interpreter in Jane to prove it, which is maybe way too much work.
Yeah. Yeah. So actually, the thing is, if you add type annotations, then it is helping me. But I add type annotation myself also. There is a library called Firefly, which does it. It does not depend on it. It check if that the integer or list or whatever it gives, it fits or not. But if it's throwing error, then it would remove it and it would fall back to Lean's interpretation of that type itself.
But if you don't have any type annotations, is your transpilation as good as adding them?
Yes. Yes.
So type annotation make no difference.
Type annotation from your side makes more difference. But I am still doing some type annotation from my end. Now, for every function that you create, I'm creating two versions of the same thing. One is provable and one is computable. Now, the difference is mostly inspired from the famous floating point, right? So a lot of tactics can't really work on floats, right? So you would need to convert into rationals or lean, sorry, not lean, but rationals or reals, right? So, and of course, like functions like tan, logs, exponential and all, you can't pass on floats. You would need to pass on real numbers. So they become non-computable because real numbers are not computable in lean. So what you would do in that case, well, you need to have a computable version as well as a provable version. So I will show two examples. So before that, I'll just say I'll just show the examples for better view. Yeah. So this is a Euclidean distance example. So if length of P1 is not length of P2, then raise. Otherwise, do this list comprehension and return that. Right. So this is a provable version. You can see a non-computable tag around it. So very minor differences between the codes, but this you can use for proving always, but you can't use this for proving because right now these are integers that we have taken by default, right? But for example, for floats or real numbers, if you have any fancy functions, you might want to compute on it. So the difference in these two things is dash rn. So these dash rn apostrophe rn rather is something that we write so that this is runnable and that is provable. Nothing is provable and dash rn apostrophe rn is runnable.
Code doesn't run.
Not always. For proving. Okay, so there's a difference. If there is possibility that a function when you write, you can prove things about it, but you can't run it. So for example, take real numbers. Lean is so strong that it's able to prove mathlib, like all the mathematics of undergrad and so on. So you would need to support real numbers, right? How would you compute real numbers on a computer? Right, you can't do that. You would need to use floats. But now a lot of theorems you can't prove about floats, which you can do about real numbers, because floats depends on how you represent on the computer, basically, sort of. So that's why I made two parts of this. One is runnable and one is computable.
But then instead of using real numbers as is, can you be something like tri-state numbers or something that
Sorry?
tri-state numbers or some fit mass numbers which allow you to properly model like
But then you would need to prove things, right? I'm using mathlib for proving things. Lean has lots of theorems about rationals and reals. I would need to, copy mathlib in that version, or like something I would have to do, which is like more complicated, I think.
So now Lean has 4.31 something called float model, and they're starting to have IEEE floats. But the reasoning here is to avoid logical error, not to avoid accumulating rounding off errors. It's not supposed to be universal. It's supposed to be making silly mistakes in LLM generated data science code. That should not depend on whether you use real numbers or float. The assumption is if the real number program is correct, the float program is correct.
Yes.
For the use case that is covered here.
There are very minor differences in these two. The differences arise mainly from floats.
But you're letting so far floats were usable because of the system.
You can't even lose 0 plus 0 is 0 with floats.
Correct. But that's because of the system representation.
Yeah.
No,
The
because you
way-
know the thing is not true, right?
For
Floating
float-
point, addition is not commutative with floats. Multiplication is not associated. Basically, no theorem you would want to know is about floats is true.
You might think 0.0 plus
You might
0.0
think
is
square
0.0
root,
star, but
square root and square, you won't get the original. It's not just the representation. No. So that's what you're saying, that you have a real version and a float number, and we prove theorems about the real numbers and assume that then holds for float numbers in our use case. People are having float model.
It won't hold because of the because.
That's correct.
So
you
you're using the I1 just to run the code, just to run to get a
just to give you an output of, let's say, if you want to train a model in these with the code that I convert, then you would need to use that apostrophe rn function. So the differences are, is provable always usable for proving things? Yes. For computable, sometimes. Right. If the function is not complex and you're just doing x plus 1 then return x, then of course you can compute that, no problem. But as the more complex you go, maybe not. And is provable computable? Sometimes. If R is used, then never. Right. And computable version is computable, obviously. And there are some differences, like for example, for proving things, you don't care about print statements. Right. So I've added a no op lines for those, which does not depend on IO monad, but computable will need IO monad support because you want to print out. Okay. So how much Python I have converted. So I'll just go through it overview. I'm not going to go in detail. This is just showing what all is done. So a lot of data structures, a lot of functions, a lot of exceptional handling, object-oriented programming, list comprehensions, control flow, all this is done. So very quick look. So you have a Fibonacci, which does a recursion, and it goes through a partial Fibonacci recursion, and it converts into Lee. Okay, loops work. Okay, right. So some list comprehension based examples and some list and string operations also, if you're curious about slicing, indexing, and commonly used functions like upper, lower, they work great. So again, all these things like pie size, pie string, upper, all these things had to be manually written. But they depend on the Lean's own upper function. But then according to Python, I had to do something so I can mimic Python behavior. Exceptional handling. Again, here there is a difference in provable and computable. The difference is because I don't really care about printing out any errors and all. I just need to, for proving things, I just need to know ki haan, it goes in that branch. But for the computable version, I need to properly throw errors. So that's why the difference is, but mostly the code will look alike.
So if the left-hand side in a different monad, it only,
It does not use IO monad.
it does not use I. So it's a monad, but it's a different monad.
Yes.
Some only accept and state.
Yes. No-op does nothing, it's a no-op.
In the future, it,
But
Petros
here
is-
it's like pipe print IO and there is pipe print no-op. So this depends on IO monad, that does not depend on IO monad.
but in
Because
the-
I don't need to, yes,
Sir.
go ahead.
I'm just saying, but Petros is working so that it will go into the state. So if you want to retrieve the prints, you can, not too distant.
Yeah, I mean,
it will become.
if you see this, the arguments and all, I'm writing everything, but I'm just not printing.
It will go into the state in a not
Yes.
far in the future. If you want the output.
Right. So some example of object-oriented program is a very small program because this is a very small slide. So class point, init, norm, and you can write everything and you can compute also just like normal stuff. And one thing about classes is like you would need to know, like for example, there is another class with the function called norm. So how will you differentiate it? So this is basically like the same way namespaces work. Right. So I have written like point.q, point.norm sq. So this is just like how you would use namespaces. So basic inheritance also works, but polymorphism and all these complex OOP yet to be done. Okay. So as somebody was asking, NumPy library and other libraries, how do you support this? So right now we support NumPy, Pandas, SciPy, math, typing. These libraries to a good extent are supported. And how would you write a library in Pascaline? Well, you just write your representation, your function, and you just match that, okay, in my AST, if a norm comes, then you just use that function. So you just create a mapping, and that's all. You don't have to touch the core library of Pascaline at all. You just write another library, add mappings, and all good to go. So it's very easy to extend any libraries or any extra code that you want. So
Sorry, saying that libraries themselves are not touched in.
no, they are touched. I'm saying if you want to add more libraries, you don't have to go and write something in the core of Pascaline, but you can just, it's basically how I will integrate your library into my Pascaline code. I'm just saying it's like you can just map the function names and that's all you have to do.
My comment there is that maybe we should have an iterative based thing. Can you go to the previous slide?
Yeah.
Instead of having separately the map,
Yeah.
when you define the function, you can maybe have an add something so and so with it.
Add the imp and grind.
No, it's like add implements add Python and put the name so that before this, so that it automatically picks it up from an environment extension. I think we'll do that. We'll do that. That might be more elegant. I mean, that's a little local. Meaning where you define Python, you can give the Python name right there.
I can do that. I didn't think of it.
Yeah. Sorry, just make an environment.
Clarifications. So like two things. So for pandas, let's say if we conduct operations on data frames, and there are things like
Are you going into the details of how I implemented pandas? Then we can talk about that after this. Because that's like how I implemented the library. So we can discuss it afterwards. I think we don't have too much time. Was that your question or something else? Okay, go ahead.
No, so like firstly, how do you make sure like the errors match? So like if there's a shape mismatch, how is that done within your lead code? And secondly, if there is like a data frame or there is like a NumPy array, does it define a separate type for those things, and can it do that class inference like convert a list to a NumPy array or vice versa?
Second question, yes. First question, no. So matching the errors part, I'm not doing that. I just throw an error with a little bit of line. Okay, this is coming from this function. I have not modeled the exact Python error outputs. And for the second question, yes, we have type plus inference for NumPy arrays and pandas reference.
That's a question if you plan on extending it to like on this very scientific libraries. Because from what I can see, the analysis used would actually really help with the cases like how the SSL defers the very 18. Because in those cases, I mean, SSH is the very first thing if you're ever getting. So a system like this can through that which
Yeah, possibly.
use it, but because talking about it that way, it isn't effective. Planning implementing such a verification to those images, but that's like a bad actor actively trying to sabotage code. At case they would override on this. That was a bad relation in the listing people. This is the true. Yes, over is oh, the SSL was so like. I tell this I would take the perfect scene of this production.
Formal verification works very well, but the Python is a bit of tricky. So this is another question.
There is a like Rust Lean libraries and all.
Third project was regarding the vulnerability like the real example. Those as well. They factor into it that you could hire a human to check it, yes, but the amount of time the resources is astronomically larger than if your program is able to be correct. So that's what plan to extend it because those as well, other than just like
But is that Python or is that information?
That's a different language.
No, I mean the being open SSL was that is not the saddest part. Also, other people are working with Rust in your sense. So this is plus. Yeah. So yeah.
Yeah. So well, that if there are different languages, then you'll have to go different routes because you'll have to convert that to Lean and then verify stuff. But you can like get some architectural ideas and what's going on and how would you do it because Python is a beast to tame. Rust is, I would say, fairly easier to do because it supports static typing and all. So
That's fine. Say that it's a part of it. And you also said that you support the method. So you support the methods of the specific traits that pandas and NumPy provide, like NumPy arrays. That you give say like different implementations of their internal methods.
yeah.
Okay. Second,
Question. One thing that I have not covered all of them, but only the most commonly used. ones. Yes. I have not like copied the source code and converted that to Lean. I have not done that.
and the spring time. I'm not aware of this, but does the spring time of Lean subsequently equal?
Oh, yes.
Then that's okay. And the third thing was that I can you just use the required intro syntax to decorators when you were writing? I think was that or be much more elegant.
Decorators.
Yes, just read about what
Great.
decorators.
I know that. Sure, actually. No, but then how would I implement invariance? Like for example, I have multiple loops in a code. Then how would I then identifying which invariant belongs to because I can write one loop, 3 invariants, another loop, 2, 3 invariants. Like then I have to mark a loop, and then I could have nested loops also. Yeah, I can have nested loop also, and then let's say one invariant is outside a loop and one is inside the loop. I'll have to mark everything. I think like going around marking things so that Lean can understand the basic stuff instead of, which is marked and unfolding that might be complex. I also thought about like writing it in comments instead of just the.
I hate
But
that
but then
because
ASP will help.
those comments are to be
Right. In case comments get deleted, and with the bad solutions. ASP also no, actually comments I had to support manually. ASP doesn't support them. I had to do comments manually also. Okay, so some showcases. How long does it take for an average Python Python to Lean? So some of the codes in example are in 200 lines, 300 lines, 400 lines, and all of them, including checking verification, took 5 seconds, 7 seconds, including the theorem verification and converting to Lean. Meanwhile, if you just ask LLM, the first prompt it will give you, okay, thinking will come in 5 seconds. Right. So, and you can, sorry? Yeah, but you don't need to think anymore.
Yeah, I know.
Yeah. So, of course, like Lean is a bit longer in terms of writing than Python. So, around 2.5 or 3 times the length. But then Python is like list comprehension. You just like 1 line of code for 10 lines of code. So, you can't expect anything. So, some showcases. So, dot products. So, this is from some orbital example that I made, some orbital physics. And CNN also, I tried training a CNN. It worked great. So you can write CNN. If I had my laptop on, I would have showed the whole code, but sad. And some NumPy related operations also, they are converted well, and you can run these things also. Okay, so maybe I'll not go into this. These are some design architecture choices that I had to go in between, but I'll just flag one couple of things.
Did you have an example with proof in your slides or not?
I showed a proof example
Oh, yeah.
before also, right? I'll come more later also.
Oh, yeah.
So one thing is I can't cover all of Python because Python doesn't care about types, right? So it can literally return anything. And there is literally type called any. So you can't do anything, and it's gonna be insanely hard to model all that in Lean. So that all is not done. But if you tame your Python code nicely, then maybe you can use Lean. And one more thing is like if you give any Python code, it will give out a Lean code, but it will also, it might show up Py unsupported. So instead of throwing a compilation error or something, it will just write Py unsupported, and whatever that line it couldn't convert, it will just write that. So you know, okay, maybe this is not converted yet, this is not supported yet. And you, let for example, if you're having agentic AI code, you have some warnings and logger lines, and I don't care about those. So that can just be unsupported, and I don't doesn't matter to me. And this is just a no-op. So all good. Right. And second thing I wanted to flag is length function. Length of high is 2. Length, same syntax. Of 1 to 3 is 3. Length of a dictionary works. Same syntax, multiple types. How will I do that? Right. I can't write pi length of one thing. Then I have to write pi length string, pi length, something like that. Yeah, but then there is a something called Lean, something gives me called type classes, and I can just write a basic class and then have instances for it, right? So instance, if the input is string, then do this. So I can actually do that, and I actually did that. So Lean works.
Is it also like possible where you create a type class like just for like those kind of operations like LAN, and then you cast those other type classes to that type class and then apply LAN?
Yeah. Okay. Like iterables when you have to implement them. So iterable for a list, iterable on a string, iterable on a dictionary, iterable on your iterable, that all can be supported. Okay, so limitations, not all of Python. Again, one return type or function you have to do. And proofs, which I will talk about. Well, it's best effort for now, and you can't prove everything, but we have done some good research using tactic like my made tactic called tasting pasta, and something Lean gives called MVC gen, which is a whole logic based tactic, which I will explain a little. And well, and libraries are handwritten, so you'll have to convert lots of libraries if you want to support lots of Python. Right. And anything unsupported gets written as Py unsupported, so you won't see like a compilation error or I just want something, don't give me everything. Yeah. Okay, so now comes the proving part of the things. Right. Now we have converted Python into Lean fairly nicely. Now we want to prove things about it. Now there are two types of functions. One is in layman terms, complex functions and complex looking functions, and one is simple looking functions, right? Simple looking functions involve, in my language, assignment statements, basic operation, if else, return, right? Those things, thankfully, can be written just like simply like lambda a to lambda b, where fun is like basically a lambda expression, and you just do the operations and return it, right? If else also works. So these become a part of non-monadic version of the conversion of your function. Meanwhile, if you have IO based statements or loops or exceptions or bizarre stuff, then you would need to go into the monadic ones, right? So if you can see in terms of proving things, we can prove equalities, inequalities, basic identities. The tactics that we use are, well, I just use taste. And it's the best effort tactic, but we can extend it using more formula, more proving methods, but sure. And for monadic verification, we use core triple based proofs and tactics like MVC and taste we do. So when do we go for monadic ones? Well, when you have loops, when you have mutations, pure functions don't allow mutations, so you need to go to monads and raising, IO exception handling, all these things. And when you want to go for contracts based proving, then also you would need to go for monadic verification. Right. So why even lower into a monad? Because pure functions don't have side effects, and things like printing statements or mutations, these are sort of side effects that you can't do it in pure function because it's not allowed. So that's why you lower into a monad, and we have our own, like for example, for exception handling, we have PyExcept, PyException IO, which handles the similar way Python have exception handling. So the trade-off between lowering into monad is, well, extensibility. Proving pure functions is super easy. Like the way you have been proving so far, it's all pure, right? But when you go into monads, things are harder to prove, but it's like you can write literally anything you want at it. So extensibility versus like the hardness of proving part, that differs. And I think we can tame that beast also. So, okay, now the question arises. I've given you a Python code. How do I even mention what I want from it? Like if I want to prove something from it, where do I even mention that this is what I want to prove? The lean won't start dreaming, oh, this is the thing that this guy wants to prove, right? So you need to mention it somewhere. So that's where the contracts part come in. So annotation like requires, ensures, invariants, decreases, or even a plain assert statements, these get all used and written into theorem statements, which are proved. And as from Ilyas Sarvi's talk, you would know, and also Professor Deepak's talk, that requires becomes the part of preconditions, ensures become part of postconditions, invariants are used in between the proofs, and plain assert statements are plain assert statement which you just write as to like a theorem, which you can, of course, you can use those contracts, right? So LLM proposes the contracts. I trust them blindly for now. There are better ways of using contracts and putting contracts, which I will look into it, but I have yet. And yeah. So this is before Python plus contracts. This is the factorial function which I have requires n greater than equal to 0, ensures that result is greater than equal to 1, and some invariants. Not a fancy ensures, but something, right? And this is the lean converted function. So I just use ensures and requires as a part of my precondition, postcondition. So I don't write it here, although I can write it. And invariants, I just let it be. Right. So now I would like to prove them. But again, as I said, it's best effort. So if you remember the previous sum to n example I showed, I was able to prove it. But there is a tactic that I had written, taste, which tries along a lot of things like grind, sim, and linear induction, like SQL you saw, but on steroids, right? And of course, I asked Claude to make a steroid version of that. So this is something you can prove. Very simple. Like if you have an assert statement of a determinant, then you can use taste, and it will show that, well, You saw that. Yeah, goal accomplished. And on the info, we will see that this is the proof. So it will come up with the proof for you. But taste might not work always. Like for factorial, it will. So MVC Gen, if you know, create sub goals for you, right? So sub goals in the sense the invariant that you pass, does it hold before the loop? Does it hold at the at the every iteration of the loop? Does it hold at the end of the loop? And so on. So it creates few goals for you, and you need to prove all of them, right? So some of them which get proved are written as like that. Otherwise just throw sorry. So after MVC Gen, I just use taste question mark and it gets automatically converted into that. So multiple goals also it can do. So MVC Gen, as I said, that it uses whole triple based things and you can prove things about it. This is the sum to n example that I showed, which taste and MVC Gen together are able to do. So these are loop invariants that are right from there. So these are converted to this. And these are some helper lemmas that you need to write for supporting range function or while loops for better understanding Podly.
Abhi is saying which he should be translated as quick. But that's critical, technical, otherwise you're pushing it way because my path on.
So I will show you an example later. From my laptop, maybe I'll not be able to present it, but I'll show you separately. That you give a factor, let's say you give a normal function, you ask Gemini or Claude to write invariants in it. Now you will be able to pick those invariants and feed it in the theorem. So you would, so your question was that should I mark these as invariants? Well, you need to feed the invariants in the function, in the Python function, so that it's able to pick it up. Does that answer your question? I don't think so. Is there?
No.
No.
You can't deterministically tell it. So you have to guess them. So intuitive kind of.
What are the properties?
Invariance for every loop. So the three main properties of invariance is that for at the beginning of the loop, that invariance should satisfy. For every iteration, it should satisfy, and at the end of the loop, it should also satisfy. So these are three main conditions that you need, and these are also the three goals that MVC Gen asked us to prove. Every iteration, before and after.
The Ilias experiences that LLMs are very good at guessing invariants. On very large scale, Ilias Sergey has used this kind of things.
So
empirically, they're good at it.
So better the LLM we use, the better the invariance we can get. So that's the end of my presentation. So I recap that we transpiled Python into Lean to a pretty good extent. We were able to prove things about it, compute things on it, and we had some usage of our taste tactic and MVC Gen for monadic verification. And we used LLMs only for proposing the contracts. So thank you. Any questions? Yeah.
I'll take Zofir at with them without questions. So I think one thing may be worth checking, these LLMs may silently change your program in addition to introducing invariants. So maybe we should have a deterministic check that the ASTs coincide modulo invariant, which is not a hard thing to check, but
I would need to have more checks because invariants themselves have to be placed at one part of the loop. You can't place invariants randomly across the loop.
LLM doesn't do evil things when you ask it to only introduce invariants. It's, I think, a check worth having.
A check worth having, sure, I'll do that. Yeah.
How does this oppose contrast to, say, doing a shallow embedding in Lean and using something like Velvet or Whale or something like Loom to kind of do what you want?
Well,
is this thing objectively better, or is this?
I think you would be able to answer that.
Short answer, when we started thinking about it, I even considered that, and it's too hard to embed all. Shallow embedding of Python and Lean will take a lot more work. Yes, I mean, the result will be better than doing it two steps like this. If you literally did a shallow embedding of, there's been chatter on Zulip for a long time about this. Maybe Malhar will work on something like Gap, But actually, I mean, it would be great to have a language on the size of basically a Lean and Python interpreter in Lean would be great, but this approach is a lot. I mean, first, this is incremental, tender incremental.
For similar languages, it's just SQL maybe.
Yes,
Or
but we can embed.
we can embed it.
Python is a bit too big to. I mean, that would be better, but a lot more work.
Yes. Plus one more issue was this is not a logical issue. We are working on 4.31 version, and that Loom and all these things are stuck at 4.24. So we would have to version issue manage and
Context are actually neat.
no, not yet. So right now, yeah, this problem itself is something that everyone is exploring into. So I can, for me, I can just take the state of the art and plug it in. I just need to count.
Get down to the
See, one thing is cause of failure is sometimes that the tactics are not able to prove it, right? So you need to manually write proof or ask Claude or Gemini to prove it for you. If they are not able to prove it, then you can think about if the insurers and all these statements, they are correct or not. And if they are not correct, then you can report an issue on the GitHub.
Well, the transpilation coverage compared to the subset on which are able to prove useful things of it. Are able to prove useful things about everything that you have transpiled. Okay, on all concepts you're able to prove.
Yeah.
Okay.
So whatever I've written, all these things are based from Lean. So Lean's implementation, I just tuned them according to this. So when you're doing same and all these things, I've in the backend, I've marked attributed all these things with simp and grind and so on. So whenever, so I can't write all the theorems in one place, right? When I have simp, I can't just go big list. And sometimes even if you like write the big list, sometimes it won't work. Right? It might simplify the wrong way. So
you're able to support all concepts which you have transpiled in
yes.
proving theorems about those.
Yes.
So that Python can return anything in any branch. So you don't have a concept of type returns. So you can just like import ground house rule on the file and direct saying that every function should have a return type annotation by type classes allow that. And then just use it in the 50 if all of the branches that are returning anything adhere to that type or not.
Yeah.
I think that would work. Then you would run into this problem of supporting like n different return types on save and
See, for right now, if you do that, the code will convert, but compilation issue will throw. So either I tell the person that oh your code needs to be factored this way, versus I say this is the code so far, and by the way, there's a compilation issue which anyone can click it and they will see the error message that it expected a different return type. So Lean itself here is showing that it expected a different return type, but you're getting this. But for other branches, since the return type was, let's say, integer, it was fine. So I don't really need to do that, but I can throw an extra warning, sure.
So in principle, if, for example, you have different things, all of which support linked, which is an example you told me, the return type could be some alpha where alpha has the type class length, right? You could kind of try to find a supremum or infimum in a lattice and return.
Yeah.
It will take work, and I mean, it will take work and lot of work for maybe not that many use cases, but it's something where one to try to take the strongest return type if it's not unique as a variable, which is a type, and all the type classes that are common to the types that different return types that you. Yeah.
Either it returns an int or a string.
Yeah, that's one thing you can do, or you can look at all that is the type. It just returns an alpha, which is a type. That's the nice thing with Lean, and alpha is part of the parameters, and alpha has all the type classes that you will use, which are common between the different things. I think that would work smoothly, but it's not easy to implement. Yes.
There was more strong
Right.
type systems of more.
Yeah.
You sort of wrap all of specifics if you are
Yeah.
strong.
Yeah. It's like I'm fighting with Excalibur with a dragon, but it just depends on how good my soldier is.
it's your driving DSLs which
change Python to NLP in my and
Yeah.
it's what it will if the
Yes.
user is not willing to help you with that.
Yes. So that's the beginning thing that I told for LLM generated sane Python code for everyday usage. In everyday usage and for production code, you usually don't do these fancy tricks. You let, if you want to return different things, then you have different functions for them. Right. But for everyday home code, then shall do. This is how you would like to, you would prove things with. So this is the precondition, this is the program, and this is the post condition.
Okay. And it automatically does.
And it picks it up.
Yeah, no, I think to connect with the earlier talks, Velvet and MVCGen are the two monadic verification frameworks in Lean. And they are collaborating with each other. And Ilya just was saying that Loom is now part of Lean Core 4.31, not Velvet. We considered both and we will try to have multiple ones, but we'll have to wait for Velvet 2.0 because they have not updated the tool chain from 4.24. We don't want to be stuck with a antique version of Lean. Antique is 6 months old. These are fast moving where the grind is much weaker, for example, and various other things. So currently we only target MVC Gen, not Velvet, because till Velvet 2.0 comes, then we should ideally target both of them.
Every language has this.
Tooling that
At least AST, everybody has.
because of supporting editors and compiler tooling, and so on, everybody gives you me. Yes.
Some kind of advice that
That's the goal. So we already have multiple claims and there are many things we want to do. One of the things is most systematically target minimum complexity and it's easier to verify. So we try to generate pure code. If we fail, we jump to monadic code. We'll want to make that kind of choice at many stages. Similarly, exactly as you said. So Anirudh discussed this and we came up with this idea of two functions, one of them to prove and one of them to compute. Why not three functions? One of them in Velvet, one of them in MVC Gen, and assuming it's monadic, and if you prove any of the theorems, either framework proves it, you know you're proved it. Because they're actually, so it's not that you're actually improving the thing. So maybe line have a switch, why not generate both and try both? Since it's all programmatic. But
And we don't have to do
we
anything
consider-
extra for supporting our core library because it's in Lean, so it can still go there and read it on. It's just how the syntax and how the proof structure is there. So Loom solve, you should be able to use it.
Look, yeah. And also the great thing is syntax is first class in Lean. Lean has very good support for syntax. So if you just import Velvet and it's understand Velvet syntax as well. So we can do meta programming without really risk of errors with many frameworks. If we don't have import, if we import Lean, we'll have MVC Gen just because it knows MVC Gen. So it actually was very smart in this respect. So yeah. But yeah, so there are many improvements like this where basically to increase the scope of what we can prove. What can be translated, Aniruddha, with help from Swarnabhu, have basically covered a lot. I don't think extending that is not much bang for the buck. But what we can prove is, of course, one has to keep on improving.
What is the most useful thing that you have proved so far?
Oh, I can show it in a proved so far.
Yeah.
Oh, I don't have a proved so far thing, but I can have a converted so far thing. So I wrote a CNN model.
Okay.
And I converted that one shot, no errors in Lean. And that worked. The outputs are exactly same because I'm converting the same thing, right? So I have a good example for conversion, but maybe not for tooling it. The proving best example would be these small things like summing or analyzing a normal thing, factorials maybe, something like that. So I'm writing just NumPy based CNN because supporting torch. Torching I have not in, but I can possibly integrate it. Yeah. I was looking for pandas library. I was looking for NumPy library, but NumPy one I found, but it was old and unmaintained, and a lot of sorries were there in the theorems. So I got disgusted with them, and then I wrote myself. Torchling I can look. Pandas I didn't find anything.
The only danger with things like Torchbeam is because these people, they have a conference paper, then there's declare victory and stop maintaining it.
Yeah.
So for all you know, they're on 4.25, which is what was the version at the conference.
So one
I
thing,
don't know if they're
one
maintaining-
thing so far I don't like about using external libraries is that I want to bump it up to another version and they don't want to bump it up. I'm on their schedule. So I don't know what to do then.